I'm going to be demonstrating near-infrared irradiance and how well it penetrates into tissue. First, I'll start out by talking a little bit about the various types of emitters. This is actually a red light emitter. The infrared is in the invisible part of the spectrum. So if you can see visible light, it's actually red light rather than near infrared. The red light has some healthful properties as well. It is good for skin conditions. It penetrates into tissue about 13 millimeters, which is just over ½ an inch. So it's good for superficial wounds, areas where deep penetration isn't necessary. But it's not technically infrared, which penetrates far deeper, particularly in the near-infrared spectrum. This is a near-infrared laser. It's actually calibrated to work at 810 nanometers. It is very, very effective at zero range, but it's working. So normally you do contact. It also has some issues. You need to keep moving because it can actually cause damage if you leave it in one spot too long. All the original research was done with lasers starting in about 1967. This is what's called a cold laser. The more powerful lasers actually are made to cut tissue and other materials. But a cold laser is this is actually more powerful than many. It's 1,000 milliwatts. That makes it a class 4. The class 3B actually have been shown to be more useful in treating health conditions than the class 4, which is a little more powerful. The highest levels in the cold laser range are up around 10 to 15 watts actually, and they have been shown to be less effective than the lower powered ones. The 3B, which is 500 milliwatts or less, is actually shown to be the most useful for various conditions. Okay, the second emitter here is LEDs. One of the issues with these lasers is that they cover a very tiny area. And so if you're trying to treat a larger condition, you have to keep it moving, and it takes quite a while to cover the entire area. So that was basically what it brought about these LED emitters. They are much more versatile in that they come in different sizes. They can treat larger areas. They also are not quite as, they don't have the danger factor that the laser has. They don't damage eyesight. The laser in a few seconds can damage eyesight in the more powerful types. The power, which is basically what we're going to be talking about here, is measured in something called milliwatts per centimeter squared. This up here, if you can see it, is 1 square centimeter. That's about just approximately 4/10 of an inch square. So the power density is measured in milliwatts. A milliwatt is 1,000th of a watt. The power used in these devices is very low. That's what's shown to be the most effective. So another issue with basically all of these devices is they lose power drastically as you move away from the site that you're trying to treat. This one here on contact, which would be basically touching, delivers 120 milliwatts per centimeter squared. So that's just over 1/10 of a watt for power density in that little centimeter squared. Now at 16 inches, that 120 milliwatts drops down to 7 milliwatts per centimeter squared, just a fraction of the power, and it won't penetrate through much of anything. So I'm going to be demonstrating here with a couple of different types of tissue. But first I'm going to show what blocks the near infrared. Now, Tinfoil blocks it completely. Zero penetration, it's all reflected. This is my measuring device. This is called an irradiance meter. Most of them on the market include visible light, so they're not really helpful in measuring near infrared because the numbers are so skewed by the combination of near infrared with visible light, so you don't really know how much near infrared you're getting. This one has been calibrated with special filters, so it only measures near infrared. Everything else has been blocked. So my first test here is going to be to see how well it penetrates a bone sample. This is just over 1/4 inch thick. I use that because that's about the thickness of the human skull. And there's been some controversy about whether these near-infrared treatments can actually penetrate the skull. And of course the best way to find out is to simply try and see. So out here at about, I'll go within about 2 inches, my power has dropped down from 120 to about 350. I'm sorry, down to about 35.5. So now I'm going to see if at this distance it can penetrate the bone. Okay, I'm getting readings. I'm getting basically just a little sprinkle through there. I'm getting 0.9, 0.3. I'm getting a little bit. This actually is a combination of red light, which is why you can see the light, and near infrared. But there's a bit of penetration. So next, I'm going to try 1/2 inch of turkey breast, see how well it does with that. Okay, here I'm getting 2.6, 3.2, I'm getting a flicker, 3.4. So I'm getting a bit of penetration through 1/2 inch. So now we'll step it up to 3/4 inch of turkey breast. 0, I'm getting not even a flicker, nothing. Actually, I got 0.3 there for just a split second. A little bit of a flicker. So now, I've got a 1 inch slice of sheep brain, courtesy of a New Zealand sheep. It's kind enough to help in this little experiment here. So we'll see how it does with the brain. Okay, I'm getting 0, absolute 0 penetration through the 1 inch of sheep brain. I should try, just for demonstration purposes, to see what the laser does. Now the laser is a bit harder to measure this power density because the point that's being shown through is so tiny that it's a bit difficult, but hopefully I can. Okay, so I'll set it. Okay, I'm getting 52, 53, 50, 51, that range. Okay, here I am getting a little bit of penetration. I'm getting 1.46, a little bit. So next I'll try the bone sample, see what we get there. Okay, again I am hitting the spot. I'm getting a better spot this time. I'm getting 47, 48. Very similar to the 50 or so I was getting first time. Okay, so now I'll try the bone sample. Okay, I'm getting 3, 6, getting a bit of penetration. So now we'll try the 3/4 inch of turkey breast. I'm still getting a trickle through there, actually more than a trickle on the turkey breast. I'm getting 13, 14, 15, somewhere in that vicinity. I should, for just a minute here, show what blocks it in addition to the tin foil. Glass and plastic reduce it by 5 to 10%. Not a huge amount, but a little bit. So that's something to keep in mind for the testing. Now, a light cotton shirt, let me try a different Okay, I'm going from 50, 48 at about 1.5 inches down to 7, 6, 7.2, 6.6. So it's dropped to probably, well, from 48 or 50 down to 6 or 7. So it's quite a good blocker. Now a sweatshirt is even better. It's a denser fabric. So again, we'll move up here within about 1.5 inches. Okay, I'm getting here I've hit a spot where I'm getting mostly all infrared. I'm getting 68, 72. So now I'm getting, okay, I'm getting about 10, 11, something like that. So it pretty drastically reduces however much infrared these healing photons are hugely reduced. Now this is a sample of hair that I got from a barber shop, nice dense hair, which I don't have anymore. So we'll try that. Okay, it's gone from 50, depends quite a bit on the spots here, some are more productive than others, but it's gone from that to 0, not even a flicker. So that's something to keep in mind if you're trying to get a treatment with this near infrared, is that hair is a very good blocker and clothes are a fairly good blocker. So what that means is when you're outside, if you have a good thick thatch of hair, you're not getting much infrared. And also your clothes are going to block probably 85 to 90%, depending on how thick they are. So that's good information to have if you're trying to treat yourself under the sun. Now this near-infrared spectrum is very powerful. This is the major area that we get energy from the sun. Over half of what we get is in this narrow little band of near-infrared light, or technically radiance. There's certain spots that are absorbed by tissue better than others. One of these is 810, so a lot of the emitters are going to use this little slice here. It turns out that these differences are not nearly as acute as what's often promoted. What happens is there are various peaks and valleys. This is not to scale, it just demonstrates that there's a peak here, there's another one at 910. There's actually multiple peaks where the infrared is absorbed better than other areas. But what's true is that they're usually shown by the manufacturers with a logarithmic scale, which makes these peaks and valleys look really huge. When they're shown on a linear scale, it's a much more gradual, mild difference between the highs and the lows. And then over in this range here, it basically, once you move out of the photobiomodulation area, which is near infrared, then the prime mover is heat, and it's the highest in the mid-infrared range, and then gradually diminishes as you move into the far infrared. Now, there's been some discussion about basically how effective is broadband, and we'll be moving out of this narrow band emittance here that's used by the lasers and the LEDs. A laser just emits one specific wavelength. So mine here I think is 808, which is very close to the peak. It just emits that one single wavelength. There's another one that has some health benefits right around 660 in the red light range, but it doesn't penetrate as deeply. Now, the LEDs actually have a slightly broader range. In other words, if it's an LED, this 810 might actually include wavelengths between 800 and 820. Still a very narrow band. Now, these are not known, they've never occurred in nature, they're only man-made light emittances. The sunlight that we've been exposed to for millions of years is actually broadband. It includes all the wavelengths in this spectrum here. So I'm going to be demonstrating next some of these incandescent bulbs, which actually have been criticized sometimes because there's only a small part of their radiation which is in the near infrared. However, what's true is that that small part is hugely more powerful than that emitted by the LEDs or the lasers, and I'll be demonstrating that. Almost all the research has been done with either lasers or LEDs, and it's been proven to work in thousands of studies over a 60-year period. So there's no doubt that these are proven ways of improving health conditions using the LEDs and the lasers. However, the incandescent lights are very, very powerful, and they throw out the whole bandwidth here. I'm going to be reading a couple of quotes here. This is from Michael Hamlin, a very well-known researcher. All wavelengths in the 800 to 900 wavelength range, plus 660 wavelengths in the red light spectrum, have health benefits. This is from the National Center for Biotechnology Information. Wavelengths of 980, 1064, 1072, and broadband infrared light have all been reported to carry out photobiomodulation effects. This is a quote from the Journal of Regenerative Medicine. Data suggests that simultaneous multiple wavelengths illumination are more efficacious than single lengths. Also, when used on different animal models in vitro and clinically, wound healing is induced by many different wavelengths. So, in other words, these very narrow bands are not the only way to get the healthful benefits of the photobiomodulation therapy. And in fact, Dr. Alexander Wunsch, a very well-known respected from Germany, believes that these narrow bands of light from LEDs actually promote something called the hormetic response or hormesis. And basically what the hormetic response is there's a narrow range where stress is very good for the body, and this can include exercise, for example, or it can include heat, can include cold, quite a number of things. The stressful response is healthy within certain limits, and there's something called the Arndt-Schultz curve, biphasic dose response. Basically what they mean is that too little doesn't work, too much doesn't work, and too much can actually create harm. Now these devices, the LEDs and the lasers, start showing a harmful response fairly quickly. Here I'll read another quote by Hamlin. A low dose of light is beneficial, but raising the dose produces progressively less benefit until eventually a damaging effect can be produced at very high light. So what's been shown is that very small amounts of this type of light have health benefits, larger doses do not. Now, my thinking along these lines is that may be true in these narrow bands, which organisms have never been exposed to until recently. We have been adapting to broadband for millions of years. So my take on that is that the broadband doesn't go over the top nearly as quickly as these narrow bands do. Wunsch thinks that they do stimulate the stress response, but don't signal the body to produce an antioxidant response. What's true is that the commonest power density is about 100. I looked at 75 studies on PubMed, which is an amazing data source for health studies, almost everything that's ever been done, millions of studies. And the commonest power density was about 100, slightly over 100. The commonest individual wavelength, or I'm sorry, power density was about 100 milliwatts per centimeter squared. Now, when you look at the dose response used, there's a measurement of density plus time, and that's called joules. Well, if you use 1/10 of a watt, which would be 100 milliwatts, for 1 second, that would be 1/10 of a joule. Most of the studies might be, for an individual treatment, might be in the range of 20 to 50 joules. 15 minutes in the sun will give you about 450 joules, which I don't think does any harm, does a lot of good, actually. So there does seem to be something that's more effective or doesn't overpower that stress response in the broadband, but that should be investigated. That I have seen no studies to validate that. Anyway, now we're going to move on to the incandescent lights here. This first one here is a halogen bulb, and I would demonstrate it, but the light coming out of it is absolutely blinding, and it is so powerful that I'll just turn it on for a minute, and what happens is when I've tried to show this, there's so much brilliant light that you can't even see what I'm doing, but I will just turn it on for a second to demonstrate that. This is a 250 watt halogen bulb. It actually has a peak at about 800, which is a very good place for a peak to be in the wavelength. It is broad spectrum. It throws out so much light that at about a foot here, it's probably up, well I can test it and see, but I'm guessing it's close to double what the sun would emit, which I don't think is wise. Okay, at a foot here I'm at 1400, 1430, 1470, way over the top, well more than double the power of the sun. In fact, you have to go back 5 feet to bring it down to a within normal guidelines therapeutic dose. So they're very powerful. I next tried a 90 watt halogen, and most of these now from here on over were measured at 16 inches versus contact, which I used with the LED and the laser. The reason is that they're uncomfortably hot. You couldn't possibly get within an inch or less using these because you would fairly quickly get a burn. So you have to use them at a greater distance. The other issue is that they're quite uncomfortable to look at. They're very bright, and they can be kind of blinding. So it's a good idea to use sunglasses if you're going to be using these, and also be aware of the distance. So for comparison here, at 16 inches, this LED light produced only 7 milliwatts per centimeter squared. Now that may have some benefit. You probably have to do many repeated doses to get very much benefit at that dose at 16 inches. That makes them a little bit unpractical in a sauna because you have to be at very close proximity to the area you want to treat with these, and that may not be logistically possible in a sauna depending on how you're sitting or laying. Now this one here produced 600 milliwatts. The sun, when I test it on a clear day, is anywhere between 500 and 600 ballpark, depending on how clear it is and what altitude. So that actually tests out very similarly too, in that when I do tissue tests, sunlight penetrates tissue about as well as this light and this light here. So I would demonstrate this one, but again, the light is so extreme that you can't really see much. So I'm going to move down here to this heat lamp bulb. This is a 250 watt heat lamp bulb. This is probably the commonest incandescent light used. The incandescent lights work through heating up a filament to very high temperatures. And they actually produce a much more powerful infrared than the lasers and the LEDs, and also the low-level lasers and cold lasers, and also they penetrate through tissue much better. So let me start out with my bone sample here. Okay, at 1 foot I'm getting 128 through the bone, 137, 138, 140. Actually, I was closer than a foot. Back here at a foot I'm getting more like 49, 50, 48, 47, 51, in that vicinity. So now I'm going to try, I'll just jump right in and go through with the 3/4 inch turkey breast. Okay, 50, 49, 48. Again, the issue here is that you have to stay back an appropriate distance so that the heat isn't excessive. Now, most of the studies that I pulled up on PubMed actually lasted a very short time. Most were between 30 seconds and 5 minutes to get an effective dose. That was using the LEDs. Now, as I said earlier, I have used these for 35 minutes, and I didn't feel like I had good results. I was using them on both my hands, a shoulder injury, and a thigh injury. And it was very helpful for all. I don't think that I was over the top, out of that hormetic zone. Okay, next I'm going to try the 1 inch. Actually, I'll double up here. I'll try 1 inch of bone and a 1/4 inch of bone and 1 inch of our sheep brain tissue. I've seen various researchers doubt that the infrared can penetrate through the human skull. This, obviously it can, using these incandescent bulbs, and penetrate much easier than the LEDs can. So, okay, here I'm getting 5.1, 4.9. I'm getting a bit more than a trickle through both the bone and the 1 inch of brain tissue. So next I'm going to try my own body here to demonstrate penetration. First I'll try in close here. Okay, I'm getting 13, 16, 18, 19. Okay, I'm moving up my forearm here to where it's about 3 inches thick. I'm getting 4.3, 3.8, 2.6. It depends somewhat at 9.5. It depends somewhat on whether I'm hitting bone, which is harder to penetrate through. Again, I was probably at 9 inches. That would be uncomfortable fairly quickly, although not with a very short duration treatment where at 30 seconds you wouldn't have any problem at all. And so let me try it at 16 inches, see if I get any penetration, because that's a fairly comfortable area. I've been at 16 to 18 inches for a half an hour at a time using these. Okay, 1.5, 0.3, 0.30, 0.5. I'm getting a bit of penetration up here where my arm is about 3 inches thick. So, quite powerful, and of course it would make more sense to give yourself a treatment from each side of your arm or leg or whatever you're testing. What I have found to be true with these incandescent bulbs that have the powerful near-infrared and also throw a lot of heat is that hands, arms, and legs can take quite a bit more heat than the trunk can. If you're within a foot here with your trunk, it gets a bit uncomfortable, for me at least, fairly quickly, whereas arms, legs, hands it doesn't seem to be uncomfortable nearly as quickly. In fact, I even do my low back, which I've had a lot of trouble with, at about a distance of about a foot. So that's something to consider. Again, out here at 16 or 18 inches, I don't have any problems for a half an hour. I've found that a 20 to 25 minute treatment works pretty well. Now actually let me demonstrate one more thing here. I'm going to demonstrate my calf, which is about 4 inches thick, just to see what we get. Again, clothing block a great deal of the infrared. Okay, here, 2.2, 4, 1.7, 3.6. So I'm getting some penetration through in about 4 inches of tissue. Probably where I'm getting very little, 0 right here, is probably because of bones that are a lot harder to penetrate. Now that's way over the top of what the LED can penetrate. Again, these have been used, tested, proven in thousands of studies. That's not to be critical of them, but they are far lower power. They throw out far less power density in the infrared range, as does the laser, surprisingly. These bulbs can be pretty hot. You want to make sure that you're touching them with something to protect yourself. They can be anywhere from 350 to 400 degrees. These last two bulbs are a new brand called TheraBulb that I've been testing. The larger one here throws out a great deal of heat. It surprisingly has less power density than the smaller 150. This is a 250 here. Now, I kind of like the smaller one because in my saunas I use a ceramic emitter for heat because it throws out this middle zone here. It throws out a lot of middle infrared, which is the most powerful producer of heat. I don't feel like I need more heat, so I try to use bulbs that don't throw out a huge amount of heat. Now, this halogen bulb here does not get that hot. It doesn't heat up much over 200, so it's pretty useful as well. Very powerful, not a lot of heat, so you can get fairly close. The downside again is it's so brilliantly bright that you need sunglasses. In fact, I would recommend sunglasses for most of these incandescent bulbs. Now, probably my favorite is this little 150 watt TheraBulb, which actually throws out 360, which is quite powerful. It's the sun, as I said, is more like 520 to 600 depending on how clear the day is. A heavily overcast day can actually block most of it. I've gotten ratings as low as 20 milliwatts per centimeter squared on a heavily cloudy day. So it really varies a lot depending on the atmosphere. There's a couple things I like about this smaller bulb. It is actually reasonably powerful. It's not uncomfortably hot at a distance of even 1 foot. And actually at a distance of 1 foot here, just make sure I'm about a foot. Okay, I'm throwing out at 1 foot, I'm throwing out 520, which is very comparable to the sun.